I'm incredibly excited to welcome Will Shih to the stage. Will has been a fantastic advocate for the nanotechnology space for really quite some time, and it was really with great honor that we gave you our Foresight Feynman Prize quite some time ago. And just fun fact, we gave 2 Foresight Feynman Prizes, where then the awardees went on to win Nobel Prizes for work that we awarded way, way earlier. So I think we're pretty good at spotting talent. I'm excited for your Nobel Prize to come up, hopefully quite soon. But without further ado, please take it away and tell us a bit about what's happening in DNA origami.
Well, thank you, Allison, for the generous introduction. So DNA nanotech has been interfacing with the Foresight Institute for about 3 decades now, and it's programmable self-assembly of building blocks that are like Lego and made out of DNA. So a key superpower of DNA nanotech is fabrication of near-atomically precise devices that fix guest molecules where you want, when you want, with trillions of copies at the same time. Shown here is a plot with time, the year on the x-axis, and on the y-axis is achievable complexity measured in number of uniquely addressable nucleotides. And over a 40-year span, it's vaguely reminiscent of Moore's law, with an effective doubling time of between 2 and 3 years. But in my view, there really have been 3 punctuated great leaps forward in this timeline. So the first was the introduction of branched junctions in the 1980s and early 90s by Ned Seaman as building blocks. The second was the introduction of DNA origami in the mid-2000s by Paul Rodamund. And the third is in recent years by my group in hierarchical linking of Crisscross origami. Now I'll be speaking about the latter 2 in subsequent slides, including some words about where we think these objects are useful. The DNA origami, you start from the long single strand of DNA, typically the 8,000 base genome of the M13 bacterial virus. And then what we do is we synthesize DNA strands that are programmed through Watson-Crick pairing in order to pinch together different parts of that scaffold after heating everything up and cooling it down into a parallel array of double helices into any kind of shape that you want. So for example, Paul Rodamund made this disk with 3 holes that his advisor at the time, Eric Winfrey, declared was the greatest concentration of happiness ever created in the history of humanity. So what are these things good for? So just to give you a flavor, my group published a paper earlier this year in Nature Nanotechnology where we introduced a DNA origami nanoparticle that can act as a cancer vaccine. So what it does is it presents CpG oligonucleotides as danger signals to dendritic cells in order to reprogram them to become more responsive to triggering a CD8 T cell response, which is what you need really against things like cancer and infectious disease. Just another example, Hendrik Dietz from Munich recently announced a raise of $29 million for a company called CPTX that tries to make DNA origami cages for capturing viruses. I should mention that we've also incorporated a startup for our work called Dory Nano and currently are raising funds. Just another example, Paul Rodamund and Ashwin Gopinath, a few years ago, they sold off a DNA origami startup called Polymetrics to SomaLogic, where they're trying to use it for omics. And so my point is that the field of DNA nanotechnology has entered into a new matured phase where now people are trying to explore commercialization of these efforts. But now I'd like to pivot to maturation in a different direction, which is instead of just trying to make things the size of a small virus, what about trying to self-assemble devices the size and complexity of cells? And we're not quite there yet, but we think we've made a big breakthrough in this area in recent years that we call Crisscross polymerization of DNA origami slats. So the first authors in the audience here, Chris Wintersinger. So here's an animation of how the process works. So it's hierarchical linking multiple DNA origami into a much larger structure. And historically, this has not proceeded with very good efficiency, but we think we've cracked this problem. And so here we have a seed molecule that's in red, that's just the size of one of these building blocks. And it kickstarts the process by grabbing the building blocks, which have to be these elongated slats. And then we program the assembly to happen subsequently where you need to make 16 of the 32 bonds for stable attachment. And by making this kind of convoluted assembly path, we prevent unwanted things from happening. We really can control the process with the same efficiency that DNA origami works with the smaller building blocks. And in this way, we can create objects that are the size, at least of the footprint of a cell. So in this case, this is an object that is 2 micrometers across. It's built from 1,000 distinct DNA origami building blocks. So it's not as concentrated a form of happiness, but hopefully you still think it's impressive in its own way. So how are these things going to be useful? We think this expansion into a new length scale will avail itself to many different applications that are not available at the shorter length scale. So for example, we're pursuing creating artificial antigen presenting cells that maybe can do a better job of expanding T cells that you might want to attack cancer cells or attack senescent cells. In another area that we're very excited about, it's a non-medical area, what we're trying to do is to create new modes of analog computation using light. So we've all grown up with this narrative that digital computation has eaten the world and is amazing, and it is amazing, but now we're finding out, if we just look at the trends, we're gonna run out of energy by 2040. So in order to stave that off, we're going to need new modalities for lower energy computation. Analog computations has come into favor, and especially using light. And so we have the premise that by using nanospacing control, we can position optically active materials in ways that can allow us to achieve really more efficient computation. We have a couple efforts. One is to make optical neural networks in collaboration with Oleg Gong and others at Columbia. And recently we just got an award from the Korean government in collaboration with Professor Sung Lee at Korean University to create quantum reservoir computers. So if anybody's interested, I'd be happy to talk about that more later. The long-term vision that really animates me is this notion that we could create cell-sized robots that assemble through a raster growth pattern, something like you could imagine in Westworld printing a cell, except they're growing. There's no actual print head. But it's still proceeding in the same way of a blueprint that you'd imagine with 3D printing. And to have a radically different method of building cell-sized robots that's different from the natural way, I think is going to be a very powerful paradigm, and I'm very excited about that. Just very briefly, I presented this as these building blocks that grow into a static structure, but we can also program in dynamics through a process of slat displacement. I'm not going to go into details about that, just show you this pretty movies here. And so we can have structures that autonomously grow, and then we have other strands that come in and basically outcompete the base pairing in order to get exponential amplification. So we have linear growth followed by internal scission, and you can create something that technically is self-replicating. Where it will become very, very interesting is where we can embed genetic information that gets copied as well. So please stay tuned. So in conclusion, I've given you the context of DNA nanotechnology in order to explain the place of our newest discoveries that we're very excited about, Crisscross assembly of DNA origamis, to now extend nanoscale control to the micrometer length scale. And if this exponential trend continues in the same way, then it's just a matter of time before we can create robots the size and complexity of cells. So thanks a lot for your attention. Happy to take any questions.
Thanks.
I love that you incorporated a moonshot. That was great. Questions, comments? Yeah.
So it seems like right now it does a lot of 2D propagation. Will it be a different challenge to be able to do this sort of 3D up dimension for the cell printing?
Yeah, thanks for the question. So we have two main paradigms for attacking that. So one is just layer by layer assembly. And so far our group has gotten up to about 5 layers, but I don't think there's anything that'll stop us. We get about 10 nanometer of depth each layer that we add. The second way is by introducing in creases into the sheet. So just like with paper origami, you could apply creases and then you could fold it up to make solid hollow 3-dimensional structures. So those are the two main ways that we plan to do 3D. And in fact, this sort of progression has been done within DNA origami itself. So we think we can just follow the same playbook and apply it at this larger length scale.
Fantastic. Oh, yep, go for it, Logan.
Hi, so I was wondering what you think is sort of the main bottleneck that until very recently has held back the translation of DNA origami-based therapeutics and other biologics?
Yeah, it's a very interesting question. I mean, there's probably multiple bottlenecks, but one of them has been, the story that we've been telling is that this ultimate very precise control over shape is going to unlock possibilities. But for a long time, it was kind of an illusion because when you put DNA origami into physiological fluids with physiological salts and nucleases, they would fall apart and get chewed up. But in recent years, our group found that a simple additive, pegylated oligolysine, could now protect the structure in low salt and also gives it some nuclease protection. There's also methods of cross-linking, other kinds of methods that have come into fore that can now protect from those kind of elements. But of course, with all nanoparticles, not just DNA nanostructures, you also have to worry about other kinds of clearance from the body. And so there's all kinds of schemes like adding CD47 don't eat me signals that I think it's not just DNA nanoparticles, but the whole nanoparticle field in general has to continue to improve and iterate on these barriers. And just in general, things take time in order to really mature.
Thank you so much, Will. And you'll also be around for answering any questions over lunch, etc.
Thank you.